In this video, I'm going to present a domain-specific modeling language and a code generator towards reducing battery consumption in location sensing of Android apps. eGEN is developed using Xtext and Xtend as an Eclipse plugin. Let's now look at the eGEN grammar and code generator. Adaptation policy is the parent entity. An adaptation policy has a context block and a feature block. A context block is a combination of values to decide the current situation of the battery and the app. The feature block helps the domain analyst to write the adaptive logic that can be adjusted at the runtime. For example, when the battery is discharging and running low, priority can be given to prolong the battery life by increasing the sensing interval in the context battery level is low, battery state is discharging, and app is in the foreground. Conversely, when the battery is charging, the impact of location update calls on the battery is less, so domain analyst can maximize the location refresh rate by decreasing the sensing interval time. Thus, domain analysts can propose as many adaptation policies as they can, and the adaptation features proposed will adjust the sensing interval when the appropriate context gets triggered. The adaptation policies should be written in a .eGen file. Our adaptive framework then generates 4 Java files, namely main activity, adaptation utility, location utility, and battery aware. Battery aware.java does the adaptive location sensing activity, and main activity simply extends this activity and fetches the location coordinates from the function onLocationUpdate defined in the battery aware class. Main activity.java can be modified by the app developers to write their own business logic. A sample task of displaying the distance covered is demonstrated in the main activity. Adaptation utility.java contains the code that alters the sensing interval based on the context provided. The battery state defined in the DSML is verified against the charging status obtained from the battery manager. Developers have the flexibility to define the battery thresholds so as to determine the battery level as high, low, and medium. When onPause method is called, the app is in the background mode. Location utility contains the code that does the location fetching activity as per the sensing interval frequency captured in the adaptation utility. Developers need to place the codes from both utility files. The battery level and charging status from the broadcast receiver is fetched here, and accordingly the frequency of the location update calls is altered. To evaluate the eGEN framework, we have selected 5 open source Android apps, and these apps are written in native Android code, and GPS is primarily used for location sensing. We have selected Nokia C3 as the test device for conducting the experiments. Initially, we had conducted cycling from the specified source to destination using Google Fit, and this distance is considered as the reference distance to analyze the location accuracy of instrumented subject application. With the help of trials, we want to identify the amount of battery saved by the instrumented adaptation policies and eGEN generated code. We had conducted the trials when the battery level was either low or transitioning from high to medium or from medium to low, so as to cover all the possible battery critical situations. From the bug reports, we found that the OpenTracks app reported maximum battery savings of 268 milliamperes and the GPS logger the least. The average savings in battery reportedly found to be 188 milliamperes. Overall, the instrumented code shows considerable battery savings on average for the trials that lasted for 12 to 14 minutes. We believe that the eGEN generated code might show significant battery savings when the apps are used for a longer time in real-world scenarios. And when it comes to location accuracy, we want to find out the extent to which location accuracy is degraded at the cost of reducing battery consumption. The eGEN versions of the subject applications resulted in an average distance measurement of 2,962 meters, which is 97 meters lesser than the distance measured by Google Fit. As discussed in the previous slide, the average battery consumption reduction of 188 milliamperes might make the 97 meters degrade in accuracy negligible. We believe that the experimental results lay a promising foundation for adopting self-adaptive location sensing policies in open source apps for balancing battery and location accuracy requirements. In the future, potential researchers can identify and catalog the domain-specific energy bugs and possible solutions to help developers make energy-saving decisions during the development phase.